Thank you, Nusrat. Hello, everyone. I am Easwar Vivek. Today, I'm going to talk about my work on non-interactive VSS using class groups and its application to DKG. It's a joint work with Aniket Kate, Pratyay Mukherjee, Hamza Salim, and Arvind Tyagarajan. So, we all know, like everyone in this hall is pretty convinced by now that threshold cryptography enables decentralization for better security, better privacy, and better availability. And the interest in applying threshold cryptography to blockchain space is evolving and, in fact, exploding as we speak in the blockchain space across multiple applications. Few of the applications that we can think of are using for threshold signatures, where we use for consensus mechanisms, for transaction authentication, and then applying threshold cryptography for verifiable random functions, where we need randomness generation for Web3 gaming, even for beacon generation for chains, even for wallet management. Over the last 2 days, we have seen several applications, including threshold decryption. So for all these mechanisms, we can think of threshold cryptography as a special case of multi-party computation, where we are trying to compute a keyed function, f of x, keyed with a certain secret key sk. But this secret key is distributed over many parties, and no single party has complete information of this sk. So one of the ways of generating the shares of this secret key among the parties is a protocol called distributed key generation protocol. So distributed key generation protocol, you can think of it as a pre-processing phase of many threshold cryptographic applications. The output of this protocol is secret shares of of a certain secret key to each of the parties. And at the end of the protocol, everyone has a private share of the secret key, and they will also know the publicly of the whole system. So each party gets a share, a partial share, which is shared as a threshold secret shared share. And when I say threshold share, the access structure, we call it as T, N, by which what we mean is that any T+1 or more parties can come together, reconstruct the secret key, and up to T corruptions are allowed in the system. And we typically consider at least honest majority in the system to ensure liveness in the system. So with that in mind, the main aim of this work is to design a versatile and efficient DKG mechanism, and hopefully a simple one too. So let's look at secret sharing and verifiable secret sharing, which is a basic building block of DKG mechanisms. The setup is pretty simple. We have a dealer D and total number of receivers, N receivers, including the dealer. And then we define a threshold, which is at least, which is less than N/2, where N is the total number of parties in the system. And the dealing algorithm takes the secret input of the dealer S as input and generates shares, N shares, which are secret shared as T, N threshold secret shares. And each of the party will be given their own respective share. And any number of more than T+1 parties can come together and reconstruct the secret share. So one aspect of simple secret sharing is that everyone will get a share, but they will not be able to know whether their share is correct or not. So for that, we use verifiable secret sharing, which allows each party to verify whether their share is correct or not. So again, the setting is pretty similar. However, we now have a broadcast channel, and the dealing algorithm, along with outputting the individual shares of the parties, now outputs a public proof, or in some sense, which comes as commitment to the shares or the polynomial. So every party can verify independently whether their share is correct or not, and take respective actions. So in the reconstruction phase, at least T+1 or more parties can come together, reconstruct the secret key, and then verify again as a commitment to the polynomial or the secret. And that's how they will know that whether the dealing was correct or not. So VSS comes in many flavors, and one of the interesting properties one of certain VSS protocols offer is what is called public verifiability. A publicly verifiable protocol offers few of these properties. One is privacy. Of course, if at most T parties are corrupt, the secrecy of the secret key is maintained in the system. But then we also have public verifiability property, which states that anyone can verify the correctness of the dealing as long as a maximum of T parties are corrupt in the system. This is the traditional definition of public verifiability. But in this work, we introduce what is called strong public verifiability, where we say that verifiability holds even when all the parties are corrupt in the system. So we formalize this property and prove the correctness of the protocol against this property. So now we say that the verifiability is guaranteed even when all the parties are corrupt in the system. But if all the parties are corrupt in the system, there is no secrecy. There is no privacy of the secret key. However, the correctness of the protocol is, can be verified and is guaranteed in the system. So let's see why is this important, or where that is, where you can see this property showing up. Consider a simple example of secret sharing, where there is an honest dealer who has generated shares and does the secret sharing. And now if there is a dishonest majority in the system where the number of corrupt parties is more than T, so they can reconstruct to a null value, or let's say they output a bottom. So even though the dealer is honest, he cannot prove himself to the world or to the system that his dealing was done correctly. So for example, if you see voting protocols, a honest voter may have voted and his vote may not even be counted if the number of dishonest parties in the system is more than the threshold T. So, but if the protocol satisfies strong public verifiability, the correctness of the protocol can still be guaranteed even when there's a dishonest majority in the system. So we're going to see, now let's see what is the state of the art of the VSS protocols and which protocols can or cannot support this strong public verifiability property. So let us first look at the interactive VSS protocols. There has been a long line of interactive VSS protocols over the years, where the setup is pretty similar. You have a dealer D and N receivers, and this dealer and the receivers participate in an interactive protocol, where at the end of the protocol, if the dealing was correct, all the receivers accept the dealing. And one of the most recent works appeared by Das et al. In last year in 2023, where they formalize the public verifiability property. So the idea is, to give a basic idea of the protocol, what happens is the dealer forwards each of the shares to the parties along with the commitment to the polynomial. And if each party verifies the correctness of the share, they'll send a signed acknowledgement. And all the signed acknowledgements are collected and quorum certificate is formed, which will work as a publicly verifiable transcript for the protocol. However, you can see that this protocol cannot achieve strong public verifiability. Why? Even if there is a dishonest majority in the system and the receivers just simply does not supply the acknowledgement, you cannot support strong public verifiability in the system. Now let us look at non-interactive VSS protocols and what is the state of the art in them. So the non-interactive VSS protocol is pretty straightforward in the sense like there is a dealer who generates the shares of all the parties, encrypts each of the shares to the respective party's public key, and then generates a non-interactive zero-knowledge proof of correctness of the sharing. And then takes the whole set and broadcasts this set among all the parties. So each party individually decrypts their own share and also verifies the zero-knowledge proof, which ensures that the whole dealing is correct. So they can verify not only that their own share is correct, but the shares of everyone is also correct. So now here we can see that anyone can perform this verification. And so this protocol, this mechanism can help us provide the strong verifiability property. So there are a couple of works which offer the strong verifiable property recently. One is the lattice-based approach PVSS by Gentry et al. In 22, and then Groth's non-interactive DKG in 21. Both of them employ what are called range proofs as a part of this proof of correct sharing, and we'll delve into one of them in detail now. So by now you should be convinced that, I hope you are convinced that strong public verifiability is an important property to offer, and non-interactive VSS can offer such a property. And one of the non-interactive DKG protocols is by Groth, which appeared in 2021. Which uses exponentiated algorithm encryption for encrypting the shares. So the encryption looks like this. You have to encrypt a message M. So you first exponentiate it to, let's say, z power m, and then you do an algorithm encryption on it. So the expectation, they want to do this because they want to have the homomorphic property on the messages so that the proof of verification can be simplified. However, there is a challenge. You cannot encrypt large messages in the exponent because we assume D-log, discrete log is hard in this group, and so you cannot decrypt large values of M here. Let's say if M is 256-bit, you cannot decrypt the value directly. So what do they go for? So they go for what is called chunking. So they divide the 256-bit value into, let's say, 16 parts of 16 bits each. Now they generate 16 ciphertexts for each of the chunks. And now when the receiver decrypts a smaller chunk, he can just brute force or use an algorithm to decrypt the 16-bit value. Now he'll decrypt 16-bit values and finally concatenate all of them together. But using the process of chunking entails them to actually go have another proof showing that each of the chunk is of a certain smaller range. So which they call proof of chunking, correct chunking. So which involves range proofs and in their case an approximate range proof. So being unable to decrypt the to larger message in the exponent actually increases the number of ciphertexts that you have and also increases the size of the, adds an extra proof that they need to add to the total broadcast length. So that increases the total broadcast length. But what if there is a mechanism which ensures that I can directly decrypt the message directly from the exponent even though if the message is large? So enter class groups. So for the purpose of this talk, we can think of class groups as large groups with unknown order where discrete log and even DDH is hard. But they have subgroups where discrete log is tractable and solving discrete log is easy. So now let us look at an exponentiated algorithm encryption in the class group setting. So here G is a generator of the larger group and F is a generator of the smaller subgroup where discrete log is tractable. So now to encrypt the message M, the way we encrypt is we exponentiate we generate F to the power of M, and then the encryption looks like what's being shown. So here now I can directly encrypt a 256-bit message and decrypt the same at the receiver. So suddenly you do not have any chunking, you do not need any range proofs or proof of correct chunking, making the system very efficient and it simplifies the design a lot. A point to note is that there is a recent independent work by Caswado and David which also uses class groups, which we are going to compare against in the coming slides. So let us look at the whole protocol. So before the start of any VSS protocol, so especially in the non-interactive sense, you are encrypting the share to each of the receivers. So each of the receivers should first register their public key. So the way you typically do is they publish their public key and also produce a zero-knowledge proof of knowledge of the secret key. So here we cannot directly use the existing schnorr mechanisms because now we are operating in a class group. So we produce a proof of knowledge of the secret key in the class group setting, which is roughly based on the schnorr proof of knowledge. So once that registration phase is done, then you have the dealing phase where the dealer generates the random polynomial, generates the shares of each of the parties, and does a class group exponential algorithm encryption of each of the shares, and then also generates a proof of correct sharing and broadcasts the whole transcript. So each of the receiver decrypts their share by first directly decrypting this F power their share. And then because D-log is tractable in a class group, they can directly decrypt their own share. So the proof of correct sharing is also pretty straightforward. I'm not going to delve into the proof. But it's a simple 3-step proof where a couple of steps are schnorr-based, one in elliptic curve group and other in class group. Then when we have one simple check where we ensure that the commitment to the polynomial corresponds to the encryptions of the shares. So with a non-interactive VSS in mind, how do we get a non-interactive DKG? So I'll just show a generic construction how to go about it. It's a pretty straightforward mechanism. So I'll show it to illustrate it with a simple example with 3 parties when the threshold T is equal to 1, where at least 2 parties are needed to reconstruct the secret. So we have party A who samples a value small a and then just does a non-interactive VSS generating 3 shares for 3 parties. Then you have party B comes into the picture, does a non-interactive VSS of random sampled value B. Similarly, C comes into the picture and does a non-interactive VSS of value C. And then they forward the corresponding shares to each other. So here, party A gets shares B1 and C1, party B gets shares A2 and C2, and party C gets A3 and C3. So now, locally, they just add their shares and obtain partial shares. It so happens that these shares actually directly correspond to the secret shares of the system secret key, which was the summation of A, B, and C. So you can see that all the computation has been done locally. There is no interaction between the parties. So a non-interactive DKG can be built directly from a non-interactive VSS by simple local computation. And we already mentioned that our non-interactive VSS protocol offers strong public verifiability property, and this property is carried directly into the DKG protocol. So a strong publicly verifiable VSS implies a strong publicly verifiable DKG. So what does this guarantee? So what it guarantees is, even when there is no privacy for the secret key SK, the correct distribution of the secret key and the public key can be guaranteed. So when this is applied to scenarios like a distributed VRF, what it ensures is that even though unpredictability of the final VRF output cannot be guaranteed, the correctness or unbiasability of the VRF value can be guaranteed. And because of this strong public verifiability property, so the support for asynchronous networks comes in some sense for free. And we can also use imperfect broadcast channel for broadcasting the shares. What it ensures is that we can use blockchain now as a broadcast channel. So suddenly all the applications which use blockchains can use this non-interactive DKG mechanism, because now the blockchain can be used as a broadcast channel. So we implemented this protocol in Rust using the Biskill library and Miracle library for the cryptographic operations. I'll talk about a few details there. And then we use the BLS 12381 curve for the commitments of the for the polynomial commitments, etc. And then we actually realized the Groth21 protocol. When the Groth21 protocol actually comes with what is called forward secrecy with a binary tree encryption. So we had to remove the binary tree encryption so that the comparison is fair. Of course, once you remove the binary tree encryption, it makes the protocol faster, and now we can compare it fairly. So the Cashwater David work, we also implement their work for Rust for comparison, and then we use the hot stuff SMR for the broadcast channel. Finally, we deploy them on GCP instances with 16 cores and 16 GB of RAM. And we set the parameters to ensure a 128-bit security, and all the shares of all the parties are 256-bit shares. And with that, once we employ the BLS 12381 curve, all the commitments will be 384-bit values. And then we generate the class group parameters to ensure this 128-bit security. And in a compressed form, a class group element will take 1752 bits. Now let's look at the performance, how the non-interactive DKG that we propose performs against the other protocols. So we are showing the total broadcast length, total length of the transcript that we broadcast across the system. Here, as I already mentioned, because of directly we are encrypting instead of chunking the values, so we save a lot. However, with increase in the size of the element, so we lose a little bit. So you can see that then, at let's say about 150 parties, we are performing at least 5 times better than the Groth DKG. So this is the broadcast length we are talking about. And the CD VSS also performs pretty similar to our CG VSS. This is the class group VSS. Now looking at the DKG numbers. So here I'm showing 2 graphs. So when I'm actually performing the DKG, you don't need to wait till all the N parties publish valid secret sharings. Because at only T+1 valid sharings are sufficient, your DKG protocol can go ahead with the first T+1 values. So I'm here showing the timings for the T+1 dealings and also the N dealings. So roughly for 30 parties, CG DKG takes 6 seconds. whereas Castro David CD-DKG takes around roughly 12 seconds. Here, the red line, which is a Groth DKG, has been implemented, realized using the Miracle library. However, if you employ BLST library, the red line can come much closer to the blue line. However, one thing to note is that there is no hard and fast rule that you need to use this BLS 12381 curve in our protocol. We can use any elliptic curve. So if you use, let's say, SecP 251, 256K1, the operations are much faster. So we went for the BLS curve for fair comparison with the other protocols. Similarly, for the end dealings, for 30 parties, you have CGD-DKG taking 8 seconds and CD-DKG taking roughly 16 seconds. So finally, to summarize, what we propose is a very simple, efficient, non-interactive DKG protocol to generate discrete lock keys. I think a couple of days ago, Alan presented a DKG where they produce keys in the, as a group elements. This work, we produce keys as scalar elements. So we have a very simple design, very efficient, and the community is just getting started with the class group implementations. And we hope that with better implementations and better study on these protocols, the speed is only going to get increased down the lane. And along with that, we also identify an important property of non-interactive DKG protocols, which is a strong, publicly verifiable property. We formalize them using UC models, and we also have a rigorous security analysis. So the paper is going to appear in CCS this year, and you can have the ePrint version through the QR code. Thank you. If you have any questions, I'll be happy to take.
Thanks for the great talk. Are there any questions? Yeah.
Thanks for the talk. Really nice work. Really happy to see this class group-based cryptography take off.
Thank you.
So I had a question first. Micro benchmark-wise, how long is a 256-bit exponentiation in a class group with Bicycle? Is it like, are we talking 300 microseconds, 500 microseconds, or something like that?
I would assume roughly 10 times more than a normal exponentiation, but I need to check it. Yeah.
10 times more than in BLS, yeah. And I guess you mentioned you have this proof of correct sharing, yeah, that proves that the encrypted things are the same as the committed things. How long does that take? Do you have a...
So I only have the total numbers, but I can get back to you with individual numbers on micro benchmarking of each of the steps.
And the DKG numbers you showed, those account for networking consensus?
Yeah, networking delays. So I mean, which is level, I mean, each along with the round trip time. So from the starting of the dealing to and each of the parties verifying. So just for computing the time, what we did is each of the parties sends an acknowledgement. So when the dealer receives all the acknowledgements, we consider the DKG to be done. So ideally, in non-interactive world, there is no acknowledgement, right? But you cannot find the timing like without an acknowledgement. So that's how we complete the round trip time, and that is these are the numbers for that.
And so are you using a consensus protocol, or is it sort of manually benchmarked in an artificial setting?
No, so we run all the VSS protocols parallelly, and then each of the parties, once it finishes the VSS or finishes the DKG, it sends an ACK, and the dealers will compute the total timing between first dealing to the first completion of all the acknowledgements.
Thank you.
Yeah, thanks. But I'll get back to you with all the benchmarks. Thank you.
Super cool work and great talk. Thanks a lot. I'm also a great fan of class group-based crypto. You mentioned this work which uses lattices. Can you give us sense how it would compare with these works?
Yeah.
Like in these graphs, in these figures, on the slides, you don't have these lattice-based schemes. I just wonder how.
So lattice-based schemes, so they're asymptotically efficient. So let's say they'll start, start seeing the benefit, let's say after 1,000 users. But in the 200 or 100 node regime, they're extremely inefficient. Let's say if a single VSS here takes, So here, so this is 30 nodes, right? So 30 nodes doing 30 VSS protocol, VSS instances. So if you see, if it takes 20 seconds, there it will be going to take, I think rough mention is 50 seconds or 100 seconds of that order. So not even comparable in sub 1,000 node scenario. So, but over, let's say if you have 10,000 nodes, they're asymptotically very efficient. So then you will clearly see the difference between lattice-based and these schemes. So because this is a continuously increasing graph, and then, but their protocol probably will stabilize at some point.
I gotcha. Thank you.
Yeah, thank you.
We have time for one more question.
Hi, thanks for the talk. You mentioned at some point that with this protocol, finally we can use blockchain as a broadcast primitive.
Yes.
Can you elaborate on this? Why can we not do this with other, like Gennaro et al.-based DKG protocols?
So yeah, so when you say broadcast channel, when you say reliable broadcast channel, right? So it also like implicitly assume that all the parties will receive the output, and all the parties are whatever is. So blockchain is not a ideal broadcast channel in the sense you can think of it as a delayed broadcast channel, because the moment you publish, there is a delay before which it reaches all the parties, and all the parties may not be live to see, and you can also come back later to see the values, right? So blockchain is a slightly different model than an ideal broadcast channel that we assume for all the parties, for all the other protocols. So it's an interesting model. People are trying to model it as a delayed broadcast channel these days.
So in short, it's about combining the models or about handling the delay that there is on the blockchain or something like that.
Yeah, so it's not an ideal broadcast
Yeah.
channel like what we assume in the community till now.
Thank you.
Thanks.
Let's thank the speaker again.
Thanks.